Welcome back. This is Rob for the third installment of section 5.4. There's a lot in here. I'm going to pick up right where I left off. We were talking about finding area underneath the curve, and even and odd functions are kind of interesting. Something kind of special happens here. In math, we have an even function if it's symmetry about the y-axis, which means you can see that the area underneath this curve for this part up to the right of the axis is exactly the same as the area to the left of the axis. And that's why we're going to find the area instead of from A to B. We can just find the area from 0 to B and then double it. Twice the yellow will be the entire area. This is kind of interesting over here because the area here is going to be a positive value, where the area here in yellow is a negative area. And the space here is exactly equivalent to this. So odd functions, oddly enough, have um, area of 0, which we'll explore in a moment. So again, if it's an even function, you can replace x with negative x and get the exact value back. So if you have something like y is equal to x squared plus 5, notice that your y value will stay the same. It's still the same y value whether you replace x with negative x or not. So if you let x be 6, then the y value is 36 plus 5, 41. If you let it be negative 6, the y value is the same. It's just on the opposite side. So that's called an even function. An odd function, if you replace x with negative x, you'll get the opposite of the function. So if you replace x with a negative, then the y also becomes negative, and this has symmetry about the origin. So even functions have symmetry about the y-axis, and odd functions have symmetry about the origin. I remember that because I stick all the O's together. The odd functions have symmetry about the origin, and it's the opposite. It's the opposite of the x goes to negative x, and the opposite of y goes to negative y. If that happens, the area is 0. So here's the definition for even functions. Instead of going from a negative a to a, we'll just start at 0 because we know of symmetry at the axis, and we'll double that area. And if it's an odd function, we know that the positive area will cancel out with the negative areas. So our first example, we'll look at this. How do you determine if it's an even or odd? We could do our test. If you replace x with negative x, you can determine if it's even or odd. If I get the same function back, it's even. If I get the opposite function back, it's odd. So if you replace x with negative x, I get the same y values. It's even. So instead of integrating from negative 2 to 2, I can integrate from just 0 to 2, or again, 0's at the axis, of x squared dx. And, sorry, my handwriting's poor. I'll integrate, integrate means increase the exponent by 1, divide by it, and evaluate from 0 to 2. So for part A, I'll do my f of b minus f of a. That's going to be 2 cubed divided by 3 is 8/3 minus, and if I evaluate here, I get 0. And so the area underneath the curve for part A is simply twice, because I have to double it, twice this area. I forgot my 2. That's the whole lesson, is to double that area. So I should have put a 2 right out front here, 2 times this, 2 times this, and then I'll do 2 times this whole quantity, and 2 times 8/3 is 16/3. You may be asking, well, what if you just would have integrated the whole thing? Here's how the author did it. What happens if you just would have integrated from negative 2 to 2 and you would not have done the double thing? Well, you get the same answer. I did it over here. You can go from negative 2 to 2. You get the exact same answer. It's just a nice short way to be thinking about an even function. I don't need to integrate from negative 2 to 2. I could go from 0 to 2 and double it. And so here's my odd function. Remember, if it's odd, I can replace x with negative x and get the opposite, and surely I do. If I let x be 6, 6 cubed is exactly the opposite of negative 6 times negative 6 times negative 6 cubed. One is a positive answer, one is the exact opposite answer. But I know since it is opposite, the area will be 0. And you may say, well, again, what if I forget and I just go ahead and go through all the integration? You can. You won't go wrong. If I integrate and increase this 3 to 4 and divide by it, I'll get 0 as well. But that work is not necessary if you know the definition of even and odd functions. The last thing in section 5.4 is talking about annuities. We've looked at these interest problems before, and we've talked about how to make investments if you have an initial investment and you compound it continuously. We're using that PERT formula. But we've never talked about having regular payments or continually adding to our investment as you go along. So an annuity is the sum of the payments plus the interest that you continue to earn, but you continue to contribute to it. Whereas these formulas before, our compound interest and our compound continuous formulas, this was simply just a one-time, you put some money down into a stock and you never add to it anymore. Remember, this was compounded daily or weekly, where n was 365 if it's compounded daily. This is compounded interest. I want to make sure that you understand the difference between this now, what we're doing now, is adding regular payments, regular time intervals, equal payments. So here's a new formula. Looks a little intimidating, but it's really not that bad. I'll give you an example of this, but see, we're going to integrate from time 0 up to t, and we'll use this formula. It works out pretty slick. Here we go. You deposit $2,000, but you're going to do this each year. That's the difference between an annuity and what we were doing before when we were using the PERT formulas. So let's identify a couple things here. The rate is 5%. So the amount this time is going to be e to the 0.05%, and we're going to do this for 15 years. So 0.05 times 15. We're integrating from 0 to 15 years. C sub t is actually the amount that you deposit each year or each month or each whatever. So it's the regular payments that we're going to do. So we're going to deposit $2,000. E is the constant, negative r. We're going to use, again, our rate of 0.05. Now, careful, this is a small t. The capital T was 15 years. The small t remains the variable. So when I integrate this, I could just multiply this out. I believe this is 0.75. Oh, and the 2,000 can come out front as well. Remember, this is just a constant. I could get a decimal for this. I'm really just going to integrate between 0 and 15 of e to the negative 0.05t. So continuing to integrate, I could do my u substitutions. If I let u equal negative 0.05t, I'll get du to equal negative 0.05 dt. And so I'm going to replace dt. I've left my dt off so you can see it. I'll put it here and put it here. So I'm going to replace dt by dividing by negative 0.05. And so dt is really equal to du divided by negative 0.05, which again, that can come out front because that's just a constant. So all of this is now 2,000 e to the 0.75. I'm going to bring this constant out front, divided by negative 0.05. I am now integrating e to the u, and we know to integrate e to the u is simply just e to the u. But I'm going to replace u back with negative 0.05t, and I multiply it by this constant. So the last thing that we're going to do here is take this constant, I don't know what that is, I'll just put it c sub 1, and we're going to evaluate then this e to the negative 0.05t, I still have a variable in here, but I know that I'm going between 0 to 15 years. So I'm going to evaluate um, this by doing f of b minus f of a. And let's see, e to the 0 is a 1. So when I do my f of b minus f of a, the last thing I'll do is I'll multiply by the constant, whatever this is when I get it in decimal form. So I'm going to pull out my calculator because this is more complicated. I can't do this in my head, and I probably would just want to get a decimal approximation here. So I've typed this in. I'm evaluating e to the negative 0.05 times the 15. Then I'm subtracting off a 1 because I know e to the negative 0 is still just e to the 0, which is a 1. So I took my f of b minus f of a, and evidently got negative 0.527633. Multiply that by this constant, 2000 e carried up 0.75 divided by the negative 0.05, and I got a whopping 44,680 and no cents. And it looks like the author has the same answer. So please email me with any questions that you may have regarding section 5.4. I'll try to post a video of section 5.5 later today or tomorrow. Email me with questions. Thanks. Bye.